Yeah, thank you so very much for the introduction, and also thank you very much for the organizers for the invitation. It's really a great pleasure and honor for me to give a talk here. I already enjoyed very much this workshop, so I think it's a great opportunity to, in particular after the pandemic, reconvene, meet colleagues, talk about exciting topics. So thanks so much also for inviting me. Now, in my talk, I would like to talk a bit about reliability of AI, which I think is one major question and one major problem these days worldwide, because it's known that AI technology is not at that level of reliability which we require. And according to the topic of this workshop, I would like to also reveal in certain directions how this intertwines with low dimensionality. So why low dimensionality can also help for reliability, and then in particular in the second part of the talk also talk about what limitations AI has these days, because I think that's something which is often overlooked. In particular, concerning the fact that we train neural networks on digital hardware. And so what we will see is that there are fundamental limitations and that we might need to think about going beyond classical hardware to maybe also then analog hardware. So that's the plan for the morning. Not for the morning, but for my talk. Okay, so I think, I don't need to tell you how important AI is these days. We see, all of our public lives is intertwined with AI approaches already, self-driving cars, telecommunication, then also think of, for instance, legal issues, which is in many countries already, let's say, pre-decided to a certain extent by AI-based approaches, and then the whole medical sector, which, as we know during the pandemic, unfortunately these days became even more important than it already is. And so from my perspective, and that's also how I came to this area, because originally I was working on imaging sciences, inverse problems. What we saw was when the first wave, or maybe the second wave of deep neural networks hit us, that these methods were extremely successful in various problem settings. So in particular in the area of inverse problems, imaging sciences, this started around 2012, and we already saw and heard beautiful talks in this direction. Many problems were attacked and easily often led to the state of the art. The second area, which was much slower to be embraced, yet also extremely important from my perspective, is the area of solving partial differential equations with neural networks, because there it was first thought, why do we need learning type methods at all? Because the PDE is a rigorous physical model, so it might not make sense to take learning type methods into account. However, what turned out is, in particular, in the high-dimensional regime, these methods are extremely important, and that relates also to the topic of this workshop, because neural networks can sense the underlying low-dimensional structure. And then also, very lately, modeling. So there's this new trend which aims to use AI-based approaches to automatically detect physical laws behind data. And I think that's also a very exciting direction. I would not talk about that, but I think that's something also which we will see more about the next years. But then on the other hand, there were also, concerns about whether AI is reliable, and so there was this interesting incident which you might have heard of. It happened during one of the AI conferences where a researcher, Ali Rahimi, gave a plenary speech. He received an award and gave this plenary speech, and in his speech he claimed that AI has become a form of alchemy. He said researchers do not know why some algorithms work, why others do work, which architecture to choose. So it's a lot of trial and error. So now, certainly from a theoretical side, we are 4 years later. We have done a lot of work. There are very exciting results, which you also heard during this workshop. But still, for instance, think of the training algorithms. It's still a lot of trial and error. So, there's a great need for driving this further, because also there are problems, and here is one, for instance, article from BBC News, which says computers can be made to see sea turtle as a gun, and I think it's well known that, for instance, self-driving cars, which react sensitively on traffic signs, can be misled by putting stickers on traffic signs in a particular pattern, so then the car reacts in a different way, maybe takes a wrong turn, and so this is the sensitivity of, for instance, neural networks for modifications, sophisticated modifications of the data. And also there, we heard several talks already which discussed aspects of that type. So in general, this is a major problem these days, the lack of reliability of AI technology. And well, coming from Germany and Europe, there, and this is true also for other countries worldwide, there are now very hard restrictions on getting AI technology approved. So people aim for certifications of AI technology concerning its reliability. And it's still not clear what now a certificate for AI technology is. For instance, I mean in the European area. So from my perspective, this is actually a really exciting chance also for theoretical foundations, because from my perspective, for deriving understanding, in particular concerning reliability of AI, one has different, let's say, levels of how you can understand AI. There's the heuristical understanding, empirical, and maybe the gold standard is to really drive the theory further to get a deep theoretical and mathematical understanding of AI. And this might then also be a key ingredient for, in the end, deriving certificates for AI technology. So these are all aspects, I think, from my perspective, for reliability, which we need to take into account. So now, from my perspective, I mean, concerning theory, mathematics of AI, there are two main directions. Mathematics for artificial intelligence, so can we derive a profound understanding? Can we ensure reliability? Which aspect does low dimensionality play? And then also using AI for mathematical questions, in particular in the area of imaging sciences, and also, for instance, partial differential equation solver. So let's be a bit more detailed, which directions I deem in general interesting, and we heard already several talks during this workshop which touch some of these directions. There's the area of expressivity, which asks questions like, which approximation capacity do neural networks have? So for instance, Tommy gave a very nice talk also in this direction. There are several areas from mathematics which play a role there. Certainly the learning question, so I train neural networks, does stochastic gradient descent converge? To which extent does it converge? Which local minima are preferred by such algorithms? And also there, a lot of mathematical tools are these days used, also maybe exotic tools like algebraic differential geometry to understand the shape of the minima. Then certainly generalization, maybe the holy grail in a certain sense of theory of AI, or in particular deep neural networks. So can we get success guarantees, particularly on the test data? And so then maybe also one direction which I find personally very exciting. We heard already two talks in this direction. One, for instance, from René, which is explainability. Why did a trained deep neural network reach a certain decision? And so here, the question is, we have a trained neural network, so maybe in René's case, he already pre-designed the neural networks so that it is interpretable, but often we might have a neural network which is not designed that way, and then we want to understand which decision it reached. And then on the other hand, there's AI, let's say, for mathematics, in particular these two directions, which I already said. One is inverse problems, which was one also major topic of this workshop, asking, for instance, questions like how can I combine AI-based approaches maybe with traditional methods? And then in the direction of partial differential equations, where one main question is about high dimensionality and can we sense low dimensional structures. So what I would like to do in this talk is I would like to focus, as said, I mean mainly on reliability aspects, touching upon what one might need for certifications for reliability, but I would like to also, according to the topic of this workshop, always discuss which role the connection of deep neural networks with low dimensionality plays. And so I would like to start from an application perspective. I would like to touch about those two topics, show you some results which you obtained, and what you will see hopefully is that in the first direction you can improve the performance of neural networks if you prepare the data in a particular way, namely you already extract to a certain extent lower dimensional structures. So you prepare the data by, let's say, more traditional methods for the neural network so that the heavy load of the neural network is eased, and that way it doesn't need to do, let's say, the heavy lifting, but the low dimensionality structures are already prepared, and that way you can often significantly improve results. I would like to also touch upon this direction, which was not discussed that much during this workshop, but which I find very important concerning, in particular, this question about low dimensionality, because there, I think you can really beautifully see how neural networks can extract the low dimensionality, because there you have a very specific problem setting where you know you have low-dimensional structures. This is already in the model, and then you can prove that neural networks can extract that. I will then just very briefly, a few slides, discuss also explainability, which is a general approach to also understand underlying structures, and then in the second part come, as also the title indicates, to limitations, which I think is also very important for understanding reliability of AI, and I think this is something which is often overlooked. There are limitations of, in particular, deep neural networks, since we train this on digital hardware. And so the question is, which impact does it have? And we will see that, in fact, I mean, there might be sometimes serious problems with training neural networks on digital hardware, so we will take a computability viewpoint on that. And we will see that these problems might be resolved if we take the turn to analog hardware, because there we have much more flexibility. And so we see also rigorous theoretical results in this direction. Okay, so that's the plan for today. So let's start with, as I said, understanding a bit how low dimensionality can be an asset if it's prepared by traditional methods for neural networks. And that way also improve reliability, because the traditional methods, we certainly have all guarantees which we want, and that way, in a sense, we have an overall guarantee which we can deduce. So let's start with reviewing just very briefly, because there were already several talks about imaging sciences and inverse problems. So many problems in the area of imaging sciences are an inverse problem. So you have an operator, you have your input data, F, your image, for instance, the operator operates, you have the output G, which is maybe an image where certain parts are taken out, and then you want to invert the operator. So you want to go from this image to this image back, and this is typically done by a version of Tikhonov regularization, which you see here, and which we also saw during several talks. So this term aims to solve the inverse problem as accurately as possible. And then you have an additional, the regularization term, where you can incorporate additional properties of your solution. And one direction is sparse regularization. So I think, if I remember correctly, this was not discussed yet in this workshop. So you have a sparsifying representation system. Think, for instance, of John's talk very much in the beginning at the tutorials, a representation system which sparsifies your data, and then you place the L1 norm on, and this you use as a prior information. And so let me show you one of these representation systems, because we will use it later on. Wavefits were already discussed during John's talk, but there are a lot of other methods, and I would like to very briefly touch upon the last, which is also a method very effectively to extract low-dimensional structures of data, and we will use this to prepare the neural network in a particular manner. So this is, I mean, as we all know, the world is compressible. That's also why we have this workshop. We have low-dimensional structures apparent, and wavefits are one great way to actually extract this. So, I mean, you saw these slides many times. So you have the wavefit transform here, and the wavefit image shows that you have a lower dimensional structure underlying, which is indicated by these white areas. So you get good compression rates. However, I mean, in truth, your data, in particular, if you are in the area of imaging sciences, they have curvilinear structures. That is their key features. And so the question is whether we can design better systems for then sparsifying, in particular, images of that type. And wavefits are not that great for that, because wavefits are isotropic elements. And so if you would like to analyze lower dimensional structures, here one-dimensional structures, then what you might need are elements which are aligned with the lower dimensional structure themselves. And so this led, for instance, to the introduction of curvelets by Candes and Donohoe. And also what we introduced were shearlets, which are a system which is very much directional based. You see this here, and you have three operations. You have one operation to translate those on the image domain. You have one operation to scale it, and then you have also one operation to change its orientation. And so what you can, in general, show is, so this is the frequency partition of shearlets, or given by shearlets, and what you can see is that for particular model classes of images, so-called cartoon-like functions introduced by Dave Donohoe, these fulfill the optimal compression rate. And so if you're interested, and I was also asked during one of the breaks, I mean, we have a lot of software on that, so you can try things out. Now, we want to use this for imaging sciences, for inverse problems, but let me stop here for a moment, because I said these are systems which sense underlying structures, which are able to detect low dimensionality, and in fact, let me just review one a bit older result in this direction. What one could show, or what we could show, is that deep neural networks are in fact able to achieve optimal approximation rates of all affine systems combined. So no matter which affine systems you take, wavelets, shearlets, curvelets, and so on, neural networks are as good as those to, in a sense, give or sense the underlying structure. And not going too much into the details, basically what this result shows is that you can mimic what people did in classical approximation theory now with neural networks. So let me just very briefly discuss this slide. As said, not going into the details. So typically, I mean, you have a class of functions, let's say cartoon-like functions, whatever you want. You have a representation system, say shearlets in this case, and classical approximation theory now aims to do the following. We take an element out of our class, we approximate it by linear combinations. This gives me an error, and then I'm interested in, if I let the number of elements go to infinity, how fast does it converge? And this is this gamma. So this gives me the approximation rate, and now I can do similar things with neural networks. So instead of here taking a linear combination, I can take neural networks of a certain complexity, and I can show that neural networks then achieve basically the same approximation rate. So this shows that neural networks are able to sense underlying structures, low-dimensional structures, as good as all affine systems which we have worked on before. Okay, so let's also now take a look at whether this, what I just said, works numerically. And if you take, for instance, neural networks which are designed in this way, so these are functions from R2 to R, and you see in these compartments you also have functions from R2 to R. And then you train this neural network on a very simple function of this type, curvilinear, where we theoretically know that the best approximation would be by, for instance, shearlets. Then you see that in these compartments the network learns something similar. So in that sense, I mean, neural networks are able to mimic what we have done in approximation theory for a long time, and so this indicates that they are very good, one indication, very good in sensing underlying low-dimensional structures. So now we use this to prepare basically the neural network for the data, and let me just mention that there are many results which aim to combine classical approaches with deep neural networks. So I mean, there are, for instance, ad hoc approaches which first use a neural network, which first reconstruct classically and then use a neural network afterwards. There are approaches which combine neural networks with classical methods by breaking open the algorithm, and we also heard a talk in this direction concerning deep image prior already. So now here I would like to focus on a specific application and show you there how we can use, in particular, shearlets to prepare the neural network in a particular way for these low-dimensional structures which come. So this is an application from CT, from medical imaging. A CT scanner samples the radon transform, as you might know. So we compute line integrals through the human body. This gives me one slice of the sinogram, and then I rotate. And this problem becomes really hard if you cannot sample the 180 degrees. So these are, for instance, true in dental CT, electron tomography, and so on. So there we have problems with reconstructing because, in fact, you have a whole chunk of data missing in this direction. And so the reconstruction you get are really bad. So here you have a 60-degree missing angle. This is your original image. This is a very classical reconstruction, filtered back projection. And then if you do what I just said, sparse regularization with shearlets, it is still, I mean, something you really don't want to work with. So what can you do? Now, the first question is, I mean, how do you now incorporate these traditional methods to prepare the neural network? And for this, let's take a look at what well, I mean, not really movie, but what I'll show you here. So here you have a 15-degree angle, which you know, and you reconstruct. And if you increase the angle, what you observe is that certainly the reconstruction gets better, that's for sure. But also what you observe is that certain directional structures are visible at a very early stage. And so here, so you see this schematically. So for instance, if you sample in this direction, then these singularities you will detect at a very early stage, whereas these will be smeared out. So since you just smear them across the whole image. And so this we can now use. We can phrase this theoretically. We can say that, in fact, you can phrase the problem in such a way that what you need to do is you need to reconstruct a certain part of what's called the wavefront set. So the wavefront set is a mathematical object, and this is what I also said during the panel discussion. We used in these areas micro-local analysis. So this is nothing mysterious. It's the singularity, and at each point assigned the direction in which the singularity occurs. So a wavefront set basically looks like this in phase space. And what we are doing is we are missing a certain part of it now, which we need to reconstruct. And so everything else we can do, for instance, with shearlets, but we know precisely what the neural network has to do and also how we need to prepare the data. So we use shearlets for that because shearlets can identify the wavefront set. And so let me show you the algorithm in this direction. We first just solve very classically the problem with the radon transform as an operator and the shearlet transform as a regularizer here with the L1 norm, which is weighted. We get the bad reconstruction, but then we do another shearlet transform. So again, now we prepare the data for the neural network, and we see that certain parts, certain coefficients, so inner products of my reconstruction F star with shearlet coefficients is almost equal to 0. This is where we are missing data, and the others are reliable and perfect. So then we only reconstruct and learn those, and the others we don't touch. So what we do is we now train a neural network to get these as an input and reconstruct these missing coefficients, and then we combine both. And so if you do it that way, so surgically just using the neural network for what the classical method cannot do otherwise, and also preparing the data that way, so helping the neural network detecting the underlying low-dimensional structure, we get reconstructions like this. So this is the traditional reconstruction. This is one of the methods which trains the neural network end-to-end, and then if you combine, let's say, both, so you use the classical methods together with the neural network in the way I discussed, you can get significantly better reconstructions. And you can use this general conceptual approach also for other tasks. For instance, here, this is a very classical task, detecting edges with their direction. These are classical methods. This is what a human would do. And so this is what we can do by, again, preparing the data using a shearlet transform in a certain way, and then training the neural network on the already prepared data. And so you see very fine structures here that way, and the color coding indicates which direction the edges have. So the essence or the message here is, if you, in particular in this area, first of all, concerning reliability, it might be good to think about also incorporating traditional methods, because there we have already the deep theoretical framework. And secondly, concerning low dimensionality, if you prepare the data in a nice way for your neural network, it has a much easier job, and the results are significantly improved. So if you have additional knowledge, you can prepare the data, for instance, using a shearlet transform, you will do a much better job. Okay, so this is one direction. The other direction in this theme I would like to show is that neural networks, if we don't prepare the data, they are also still very good in sensing underlying structures. And as said, we didn't hear a talk about this, so maybe bear with me, but here in this framework concerning partial differential equations, which is basically a very universal theme if you would like to model any, let's say, natural phenomena, there we can really rigorously prove that neural networks are then able to detect underlying low-dimensional structures. So, well, I hope everybody knows how a PDE looks like. We have a differential operator. We have on our right-hand side, we have the solution U. And typically what people do now, since basically 2017, with research taking off, is to use neural networks for approximating the solution. So then the neural network is also incorporated, if you train the neural network, the whole PDE, the operator, and the right-hand side is used and encoded in the training process. Here in this talk, I would like to show you and take you to a bit more general setting, which are parametric PDEs. So parametric PDEs appear in basically any type of science you can think of. So, for instance, design problems where you have a partial differential equation and you have a lot of parameters which can be tuned depending, for instance, on the heat and on the design and so on. So you have partial differential equations of this type. You have here, again, your differential operator. You have the right-hand side. You have your solution. And everything is governed by this y, which are the parameters. And certainly what you want, if you want to design, for instance, an airplane wing, what you would like is for each set of parameters, you would like to compute the solution. So you have here your parameter, and each time you want to compute the solution. And this is a huge problem if, for instance, your parameters are in, let's say, R100. Because then, the curse of dimensionality will beat you, and you have a serious problem because the computational costs might be too high. But this is what people in that area call a multi-query situation. So each time you have a parameter, you want to compute the solution, and you need to do it a lot of times. Okay, and so now you can ask, what can we do with neural networks in this setting? So first, certainly, we need to bring it down on the finite dimensional situation. So what people typically do in this area, they have some high dimensional, finite dimensional space, I don't know, in R, again, 100, let's say, which is where you have an orthonormal basis. So your dimension of your very high dimension but finite space is D, because typically the modeling, as you said on the previous slide, and again discussed during the panel, typically the models are analytic, but if you would like to compute it, you need to go in the finite dimensional setting. And so then, the question is, can a neural network now approximate this map, given a parameter, maybe in RP? Can we compute the coefficients of the solution? So this has a lot of advantages. After we train the neural network, we get a very fast method from each parameter to compute the solution. We also have a very flexible universal approach. And it also shows, and we will see that neural networks are able to basically, are universal in that sense. They are able to handle also situations of this type. And so key questions which you can ask in this direction is, you have an accuracy. Do we find a neural network which approximates the solution up to any degree epsilon for any parameter? And also, how does the complexity depend on P, which is the dimension of the parameters, and capital D, which is the overall dimension? So this question is crucial because this would show that the neural network is able to sense and feel underlying low-dimensional structures. And last but not least, then also how does it perform numerically? So there are certain methods which already do that to a certain extent. They are very complicated. Let me just very briefly discuss this here at this point. So what people before did was, you have your solutions here, for instance, on this continuous structure analytically. Then you bring it down in the finite dimensional situation, so this gives you a certain error. And then in the finite dimensional situation, what people did was, you compute for certain parameters, you compute so-called snapshots. And from those, there are then methods somehow to deduce points which are in between, solutions in between for certain parameters. So this is something which people have done. These are called reduced basis methods. So basically you reduce the space and then calculate the solutions this way. But for several PDEs, this does really not work. It's very complicated. You don't really know how to maybe choose the basis for your low-dimensional space and so on. And with neural networks, you have a very universal method where you can basically solve all those problems, and the results are actually, I think, quite convincing. So let me just very briefly, maybe not go to all details, show you, the following. So let me just say, at this point. So these reduced basis methods, we have a low-dimensional space. So this dimension is d epsilon. And the low-dimensional space we put in such a way that basically every solution, or we assume it can be put so that every solution, every true solution is approximated up to a certain degree. And so there are methods to show that there exist such spaces, but typically it's a general assumption that there exists a space. So for the neural networks, we don't need to find it, we just know it exists. And this is typically the case. And so then, I mean, usually, I mean, these methods, so let me just not go too much into the details. So the solution coefficients in the low-dimensional space can be explicitly computed. But now with neural networks, we can basically, I mean, I wouldn't say throw this all overboard, but if we now train a neural network to compute this parametric map, what we can show, and maybe let's first take a look here, we can show there exist neural networks of this complexity. And with complexity, I mean the number of non-zero parameters. Yeah, as you see, I mean, this complexity is extremely nice. This high dimension is only linearly in here, and the dimension of the reduced space is only cubically. So there's no exponential term here, which you would expect if the cross of dimensionally would still be present. So there exist neural networks of such a nice complexity, so that the neural network function approximates my solution up to a certain epsilon for any parameter. So this shows that basically now with neural networks, we can, in a certain sense, solve this universally. And what you also see here, let me just briefly discuss the hypothesis. This is a very natural hypothesis, which basically says there exists a nice low-dimensional space, which lies in that sense that if I compute solutions for it, it approximates my true solutions in a nice way, but you don't need to know it. It just needs to exist, which is usually a general assumption. And there exist neural networks which approximates the forward operators, which is also usually true. So then, I mean, you can drive some numerics to check whether this also happens numerically. Again, I don't want to go too much into the details because, I mean, I guess not everyone is an expert here in PDEs. Parametric diffusion PDEs is a large area. And we have here our parametrization. You see this here. You have the set of parameters which are encoded in a certain way in these terms. But here you see the y's. And this is encoding. There are different ways of encoding. Some are more difficult, some are more easy. There are more easy ones, which are of this type. There are more difficult ones, the so-called non-affine parametrizations. And typically, classical methods have huge problems with those types of parametrizations. Now, what we then did was we set up, I mean, in a very conscious way, let's say a battery of experiments which were all done in the same way. We always had the same fixed neural network with 11 layers, with this number of neurons in each layer. We have always the same activation function, always the same number of training samples, always initialized with the same way, I mean, to really have, let's say, a conscious setup of comparison. And the dimension of the parameter space was set up to 91, which I think in your case, you think this is, I mean, extremely small, but in this area, this is already extremely high and very difficult. And so what you can see for certain parameterizations, you can see that, I mean, the parameter dimension, if it goes up, that then the error which you make in the test phase just goes up linearly. So again, you don't see any complexity blow up. So this behaves all very benign, and this is true also for other settings, for other affine parameterizations. Again, you get this linear behavior. Also, the training error goes down nicely. Everything behaves very smooth, very benign. And also, even if you go to the non-affine parameterization, also there things behave very nicely. So what one can show is, in that sense, the performance does not suffer from the curse of dimensionality, and it's also efficient for non-affine parameterizations. So I think this is, I mean, a great asset. What we saw there is that neural networks can sense the low-dimensional structure very well. We can prove it here, and also for this whole area, neural networks, in particular, that ability to sense low-dimensional structures is extremely effective. And so, And since we have the theoretical results, we also get reliability in that sense. So let me just, before I come to the main second part concerning limitations, I mean, just maybe very briefly touch upon explainability, because I think this is something which is extremely important for reliability and is also extremely important for revealing low dimensionality. So now we saw a lot of applications, but again, for instance, in the imaging problem or imaging application, we didn't have complete rigorous theoretical results. But I mean, explainability is one way to solve this problem, and I think this will be one key ingredient then also, for instance, for getting certifications of neural networks and AI technology. So maybe I can skip this slide because we already heard very beautiful talks concerning explainability. The main question is to explain black box predictors, to understand how they reach decisions, and maybe as compared to René's talk, here the neural network is not prepared in a particular way. It's a standard neural network which is not really designed to be interpretable, but it's just any neural network. And so one way, I mean, we viewed the problem was from, let's say, an information theoretic viewpoint. If you have, let's say, your initial signal X, if you have your neural network, then you would like to transmit in the sense also of signal transmission, the key, the crucial elements to the second person who should then verify whether it was the same neural network, the same message. And so now since you just transmit parts of it, it needs to obfuscate it to a complete image and then get the result. So this is in the setting of rate distortion theory, where you transmit a certain small part, the size is the rate, and the distortion is the error which you make. And so certainly, I mean, what you aim for is you want to drive the rate down, so you want to have very few key components in the sense also of extracting the low-dimensional content of it. At the same time, you would like to have low distortion. And certainly, you can imagine this you cannot compute. So this rate distortion function, lowering the number of key components versus keeping the error under control, this is something you cannot compute. It's NP hard, NPP complete even, and so you can relax this in the canonical way, which I think in this community is very standard. So you relax it concerning the L1 norm. You take now continuous elements for each pixel relevance scores between 0 and 1. And so just showing you maybe one image here. What you see here is that the explanation which we get that way reveals also the low-dimensional structure, which is important for the network for that decision. You see here exactly, basically, the low-dimensional singularities in a certain sense. So since we train for conciseness and aim for conciseness, then what is revealed are exactly, basically, to a certain extent, the boundaries. So it shows that neural networks, this is what they take into account, the low dimensionality. It's another instance of what we already saw before. And so if you compare now concerning how many pixels you require for a certain distortion, I mean, then these algorithms, because they are also tuned towards that, certainly here have the steepest curve. You can extend this in certain ways now, and I don't want to go too much into the details. Again, there you can extend it by taking also, if you know that, the data distribution into account, because you might not want to obfuscate by random pixels, but you would like to maybe have something which is a bit more natural. And also, and this brings me back to the beginning of my talk, you might not want to have relevance scores for pixels, but maybe for higher dimensional structures. So for instance, René showed us so blocks of pixels, and his framework was also flexible enough to, for instance, include wavelet coefficients or shielded coefficients. So here, indeed, we also then take relevance scores of wavelets or shielded coefficients. And so maybe just to finish this part with two examples, what you can do in this direction. So for instance, what you see here is an application from telecommunication. You see here a city map. The red dots are cell phone users, and the white blob is a cell tower. And the neural network computes this black and white background, indicating at each point how strong the signal there is. And now you see there is something very strange happening here, because this is an area of bad reception deemed by the neural network, but this area is right in front of the cell tower. So this doesn't make any sense. And you can ask now with these type of flexible explainability approaches, why did this occur? And the explanation is that in fact the neural network looked at those structures, and these actually have bad reception, and that led it to mark this area in dark, in black. And so the network did actually something sensible. So what we found out later on was that there was actually a building missing in the city map. So the neural network really did something correct, and we revealed it by these explainability approaches, which we wouldn't have done otherwise. And maybe just as a last example, where we now take wavelets also into account, there, what we found actually quite interesting is you can, for instance, concerning adversarial examples, detect reasons why adversarial examples occur, and then maybe prepare the neural network also for improving this failure. So here is an example where this was classified as a diaper, although it's obviously a man with a dog, and this was classified as a screw. And now, if you take the wavelet-based explanation, so basically what I showed you before, but now the relevance score on wavelet coefficients, then you can reveal what the network has mistakenly seen. And so if you now overlay it, if I overlay it, you see, I mean, this could be then actually mistaken as a baby, and then the diaper is not that far off. And this can be mistaken as a screw, and so then a screw is actually a good explanation for that. No? So now, I mean, with such a flexible explainability approach, which is also rooted in theory, so reliable itself, you can, well, maybe get some additional insights also in neural networks. Okay, so this was just a brief excursion, and let me now also come to limitations, because I think that's an area which is often very much overlooked. I mean, we see great results of neural networks, but they have limitations. I mean, they're not a Swiss Army knife, and so this is something I think we need to take into account. And this is also, for me, one key aspect actually of reliability, because if you want to have reliability, we need to very consciously analyze what we can do and what we can also not do. Yeah, so, I mean, if you look at theory, we have beautiful theory, and there were amazing talks in this workshop concerning, for instance, expressivity, generalization abilities, and so on of neural networks, conversions of training algorithms, generalization abilities. However, I mean, from my perspective at least, what we do not consider enough is what happens now if we train neural network our laptop on classical hardware. So what is maybe the sample complexity if we train it on our digital hardware, on our GPU, and in particular limit of the computability on where we perform our neural networks today on. Because, I mean, I guess everybody of you has a laptop in front of you. This is a piece of digital hardware, certainly. GPUs are digital hardware. This is what we use all over the place. So there's a theory to practice gap in a certain sense. I mean, the theory is beautiful, but I think this is something which might need a little more attention in this direction. And so the question and the goal of the last part is to examine boundaries imposed by digital computers. So what is the computable function? So think back of your CS class, maybe there's a whole theory on computability, and let's say in a nutshell, a computable function is one for which the input-output relation can be computed on a digital machine, which is typically modeled as a Turing machine for any given accuracy. So this is standard, and I mean a Turing machine is the classical model and the widely accepted model for digital hardware which we use these days. So what problems are there? Well, I mean, the underlying problem, is it feasible? Well, I mean, for that, to analyze this, we need computability of the ground truth. If we cannot compute it, I mean, we will always have an error which we might not be aware of. The neural networks need to be computable. Otherwise, I mean, we cannot assess them from a theoretical viewpoint. And also, what we need, the neural networks are computable by minimization problems, so we need to compute the mapping to the approximation, which we deem important. Certainly, I mean, if things are not computable and you see that there are problems, you can tackle that in practice. You can still compute things. I mean, you will get some output. But, I mean, you might facing limited precision in that case, and also it's a problem with guarantees of correctness. So you might have nice error bounds, but if things become not computable, I mean, these error bounds, you cannot say if they still hold or not. Okay, so as already said, I mean, the key ingredient here are Turing machines, which are a classical model for today's hardware where we train on. So the Turing machine, well, I mean, it's certainly closely linked to discrete problems, but typically, and this was again also part of the discussion yesterday in the panel, typically you have continuous type analytic problems. And so the question is, I mean, which problem does this deviation causes? And here again, I mean, a Turing machine, if you haven't seen that, but I presume everybody of you have heard that in one class or the other. So you have this tape where you have, let's say, some device which is able to move back and forward. Here you have 0 and 1, so a finite alphabet on it, and so the Turing machine is able to modify this tape, and then, I mean, the tape hopefully contains the output which you aim for. Yeah, but I mean, it's purely discrete. That's the key point here. And so there's a whole theory on what computability is. I mean, for instance, there's a definition of computable real numbers. So let me just, I mean, for the sake of giving you a bit insight, showing you this. So the definition of a computable real number is if you have a natural number on the initial tape, which you just saw, then it is computable if the Turing machine, when it acts, it terminates with a rational number so that the error is controlled. So the error between what you get out and the true real number is controlled by this 2 to minus n. So you have the accuracy first on the tape, then the Turing machine acts, and then you would like to get this rational number q up to this accuracy. And so you can extend this then to computable functions. Again, I mean, a function is computable if there exists an algorithm which gives for any computable real number and any n an approximation of f of x, again with this accuracy. Okay, so again, I mean, this is just a small glimpse. There's a whole theory, very beautiful theory of computability out there. And so what we could show is that, in fact, I mean, if you look at finite dimensional inverse problems, then in general, there might be some where it's computable, but in general, the solution is not Turing computable. It's even stronger than that. It's not what's called Banach-Mazur computable, in particular not by a neural network. So this is a disappointing result. Certainly one question is then, I mean, maybe to categorize what is still computable and what not. But in general, I mean, in a general setting, I mean, this is not computable, so what does it lead to? So in general, there exists no algorithm which on digital hardware derives neural networks which give you the solution for any given accuracy. In that sense, the output, you don't have guarantees, it's not reliable, and this could point towards why we also observe instabilities and non-robustness in certain cases. Yeah? And so as an illustration, even if you have, for instance, I mean, a theoretical bar, you don't know whether your neural network, whether the output, because you cannot compute it only up to a certain precision, will be within this error bar. Yeah, so the theory then, I wouldn't say become useless, but I mean, concerning accuracy, you might have a major problem. And for certain of these results, we actually also have bounds on how accurate you can compute, but how accurate you cannot. And so sometimes this error is within 1/4, which is actually a lot. So this is quite disappointing. So if we train neural networks solving finite dimensional inverse problems on digital hardware, we could run into these problems. So is there a way out? Well, I mean, also there, let's say, mathematics tells us the answer. And what we could show is that for analog hardware, and according to Turing machines, there's also an according analog model, which is a Bloom-Schupf-Smale machine. there suddenly things become computable. So the solution of finite dimensional inverse problems is computable on such an analog machine. So if you do the step from discrete hardware or digital hardware to analog hardware, then we might have much better and improved reliability. Again, looking now from a reliability viewpoint. So there might be a need to really reach reliable AI to actually rethink which type of hardware we train our neural networks on and where we let our algorithms run on. Maybe the pointer is towards novel hardware, and there are already very exciting directions in this aspect. I mean, I'm sure you have heard of neuromorphic computing, neuromorphic chips. There's this area of biocomputing, and there's also this area of quantum computing. So for instance, there are already quantum simulators, which, I mean, in small scales work quite well, but these are then true analog machines. Now, so in that sense, as said, I mean, it might be in general worth rethinking what type of hardware we train our neural networks on. And so this is, I think, an aspect which needs to be considered much, much more. And this inverse problem result is one instance. I mean, there are many other results you can prove in this direction. So for instance, classification problems, there are various classification problems which are not computable. The pseudo-inverse, which is the key ingredient in various algorithms, is also not computable. Also, if you solve partial differential equations, in particular, for instance, the diffusion equation, which is one of the easy type, we saw it just, I mean, what you observe there is that the solution is, from a computability viewpoint, I mean, exponentially more difficult to compute than the input of your problem. And also, last but not least, for optimization problems, there are also various optimization problems which are not computable. So in that sense, I mean, to really get mathematically reliable AI, we might need to go to, as said, analog hardware. Maybe quantum computing is one way out. I'm not, let's say, claiming that, but maybe other types of analog hardware, but I think this is something which is worth considering and worth also taking into account. The theory one derives is absolutely beautiful, but then if we break it down to practice, we might need to rethink that. Okay, so let me finish with some final thoughts, because I think my time is up. So I mean, from my perspective, I find this an extremely exciting area, AI. I mean, we see it now in various instances of sciences, public life, and also in particular from a theoretical mathematical foundation and perspective. I think it's really rewarding to work in this area. What I find also very exciting is that we see various different aspects of theory now entering this realm. And then, I mean, I discussed a little bit, I mean, which key directions I see. We touched then a little bit on some of those. I mean, we saw some results in expressivity, explainability, and also inverse problems and partial differential equations, each time from the viewpoint of reliability and from the viewpoint of low dimensionality. And so what we often saw is that low dimensionality is also the key which neural networks have to then achieve and succeed in these tasks and also get reliability. And in the end, I mean, one thing which we might need to consider more often is also limitations. And here, this is one instance of a limitation I see, which are problems with computability on low dimensional, on digital hardware, and said, I mean, in all of those, somehow low dimensionality was the guiding factor. And let me just finish with maybe one slide, maybe a short ad, because I talked about reliability, and we are very excited that now, I mean, in Munich, we have actually a school for reliable AI, the Konrad Zuse School of Excellence in Reliable AI. It's a school between both universities of excellence, LMU and TU Munich, and as you see, mathematical and algorithmic foundations are one major aspect there, but also medicine, robotics, algorithmic decision-making intertwined with reliability aspects. Okay, and that's it. I would like to thank you very much for your attention.
All right, thank you very much, Gitta. And I think we have time to take 1 or 2 questions, if any. All right, here, please.
Hello. So you use only ReLU activation function, does not any other activation function works to approximate the solution of differential equations?
Sorry, could you say it again? I didn't really...
Okay, so you use only ReLU activation functions.
I use what?
ReLU activation function.
Which activation? Oh, ReLU. Oh, really?
Yeah,
sorry.
yeah.
Yes, okay, sorry.
So does not any other activation function works to approximate the solution of differential equations?
Oh, yeah, sorry, certainly, yeah. So we looked at ReLU because that's the most common activation function. But certainly, I mean, these results, I mean, we also have results to extend this to other activation functions, yes.
Okay.
There are extensions of that.
One more question. What's the input of the network when you find the solution of differential equations?
So the input here, I mean, okay, so you don't mean for parametric PDEs. So for parametric PDEs, the input are the parameters then, if you would like to compute the parametric map. I mean, for a normal PDE, you would input, let's say, the initial data on your, let's say, unit square, for instance. Okay. I mean, so it depends on the type of PDE. So, but here our input is the parameter which we then use. I mean, and the output then, if the and the output are the points on the square.
Okay, thank you.
Hi. Regarding using neural networks for PDEs, you discussed using fully connected neural networks, but if I understood correctly, you could have used any other parameterized family of nonlinear mappings. So in this area, are neural networks really, there's like strong evidence that they're considerably stronger than other nonlinear mappings? I mean, is it like envisioned that for many neural networks are considered far superior to anything else, or is the situation less clear at the moment?
So here, I think it turns out that right now it's actually becoming very clear that neural networks have a huge advantage in the high-dimensional regime. So in the low-dimensional regime, if you have, I don't know, a two-dimensional PDE, you have optimal classical methods. There is no need for AI or for deep neural networks. But if you go to the high-dimensional regime, and this is also, I mean, concerning the topic of the workshop, because neural networks can circumvent the curse of dimensionality by sending these low-dimensional structures, then neural networks really now become the state of the art. Yeah.
Okay.
Hello, thank you for the talk. I had a question with your first work about the limited angle CT reconstruction, in which you used shearlet-based regularization. So I was wondering, how does this perform in the situation where the CT system might have some noise like scatter, blur, and or Poisson, uncorrelated Poisson noise? Is it still able to reconstruct those edges given that you have a shearlet-based regularization?
Yes, yes. So from our experience, I mean, it does, because, I mean, the problem you solve in the beginning already has, let's say, this term, this data fidelity term, which kind of incorporates problems with noise already in there. So in that sense, I mean, this kind of, let's say, takes the noise to a certain extent out of the problem. Yes. So, but I mean, then also, I mean, it's also a question, certainly, as we all know, on the training data. So here what we do, I mean, we train it from artificial data. So we have artificial ellipses and so on, and then we train on real data from a Mayo clinic in the US. And so this is already a bit noisy. So you could do, I think, an even better job if you already train it with much more noisy image. But again, I mean, this reconstruction strategy has already, let's say, a built-in fail-safe for, to a certain extent for noise. Yeah.
Hi. The last part of your talk about the limitations of deep networks at learning with finite or digital machines was very intriguing. Recently, and this was Stefano Soato, was giving the example of the difficulty of learning the concept of the number pi, because if you give the number 3.1459 to a human, eventually after 6 digits or so, a human will say that's number pi. But if you keep giving numbers, in his example, he had 2, 2, 2, 2, 2 eventually. And so it was not number pi.
Yeah.
So you had a long list of examples. The first one was on classification. Could you provide more fundamentally what is the challenge, for example, on what kinds of classification problems this is a fundamental issue that we cannot build machines with finite precision that would be able to, say, classify certain concepts?
Yeah, so thanks for that question. I mean, so we don't have, let's say, a whole, let's say, classification of which classification problems are difficult. We have in the paper, I mean, some examples of which are problematic. And so this is also, I mean, as said, I mean, for the other results, I'm not saying that, let's say, all of those problems are not computable, but I mean, for each of these instances, I mean, each of these classes, there are problems for certain situations. And so there, I mean, for classification problems, I mean, if you have, for instance, I mean, different classes and the classes are aligned in a certain, let's say, unfortunate manner, I mean, then it becomes a problem. But I mean, so we have special, let's say, special situations where we can then prove non-computability.
This would also be a problem for the explainability framework you had, because if I give you any subset of the digits of the number pi, you can't tell that it's number pi.
Yeah, exactly. So, I mean, also what I showed before, I mean, these results on inverse problems and partial differential equations, I mean, the last part basically, I mean, sets this into perspective and shows that actually, I mean, the theory which one develops there then also has a problem in this direction. Yeah, absolutely.
Gitta, over here. Thanks for the wonderful talk, and also I was very intrigued by the second part on computability. So I was wondering, you know, how much of this sort of challenge comes from the fact that we're taking real numbers as a reference. It's like I can go in both directions. So let's say, you know, John Conway, late John Conway, the discrete math guy, the group theory. He had all these crazy ideas about games that can compute any number. This Fractran game, I don't know if you know. So they are not a classical Turing machine, but they're equivalent and they're universal. And so through this game playing, he also came up with a completely new number system. It's called the surreal numbers that contain, you know, all finite fields and infinite and whatever, also ordered and so perfectly fine. And so we could just as well take these surreal numbers as reference, but then we would make our problems even harder, right? Because it would be even harder to sort of compute these numbers. And in the other direction, there's this Dutch mathematician, philosopher, Brouwer, who, you know, came up with this intuitionist math, for which now there is some evidence, actually. There's also a mathematician in Geneva who, that basically says at a philosophical level that real numbers don't exist, right? And so if we don't assume that real numbers exist, then many paradoxes in physics get resolved easily. Or not easily, in a complicated way. But like, what are your thoughts on that? You know, taking these real numbers as reference seems a little bit arbitrary. And yeah, well, that's not really. Yeah.
Sure. Thanks a lot for these, I mean, different thoughts in that direction. Yeah, I mean, certainly the real numbers are the problems. I mean, if you look at, I mean, from this viewpoint concerning Turing machines, which real numbers are computable, I mean, it's a very small set. It's in fact a zero set. So in that sense, I mean, this is exactly the problem. So if you have a purely discrete problem, I mean, then you don't run into these computability issues. So this is the problem, but I mean, so we discussed also during the panel discussion that these analytic models, I mean, have a huge value because you can drive very beautiful theory, and we know from also mathematics that if you go from the continuous to the discrete world, I mean, then own problems occur. But from a computability viewpoint, if you have these analytic models, I mean, then you might need to be aware that you might not be able to compute them in this way you aim for, and that your error bounds might not hold. Yeah.
Thank you.
Just a silly question, technical question about what you mentioned about the pseudo-inverse, that it's not computable in the Banach-Mazur sense. Would that be different if you'd have regularization so a regularized inverse instead of the limit for lambda going to 0 of the regularized inverse?
Yeah, so in some instances this might help, but as said, I mean, I'm not saying that any pseudo-inverse is not computable. I mean, there are classes of pseudo-inverse which are not computable, and so one next step, which we are also now looking at, is classifying exactly those problems which then are computable.
Okay, and if you had a regularization, would that make it computable? It depends.
Yeah, I would need to look at this. I think it's an interesting thought. Thanks for that. But I mean, maybe sometimes it helps, but I don't think it's a general, let's say, a general approach which helps, because also think of the inverse problem. I mean, there are the finite dimensional solutions we also regularize. Still, I mean, things can be non-computable.